Hi, it's time for another math easy solution. Today we're going to go over further into vectors and the geometry of space, and this time look at vectors. And yeah, let's just jump right in. Just a note, if you don't have time to watch this whole video, you can play this video at a faster speed. And yeah, this top secret life hack, brain gets used to faster speed. You could check out this link for more. And you can also download and read the notes on the Hive blockchain, and links for both will be in the video description below. And also you can watch a video in parts, and there'll be timestamps of all the parts in the description, and you can even skip this intro as I usually do. Anyways, let's jump right in. So calculus book reference, note that I mainly follow along the following calculus book. This is Calculus Early Transcendentals, 7th edition by James Stewart. Note, in the earlier videos, I used the 6th edition just for reference. And now here's a new segment here. I just included sections in Calculus book chapter. So I've made a list of the sections in this particular chapter with links to the Hive post of the videos I've already finished. So this is the chapter we're currently on, vectors and the geometry of space. And then part 1 was 3D or three-dimensional coordinate systems, and there's a link to the video. I put the link to the Hive post. It includes YouTube links and all of the alternative links as well, as including all the notes too. That's why I just like sharing the Hive post. And now we're going to be, in this video, we're going to look at vectors. That's current video. And then the next we'll have dot product, cross product, discovery project, the geometry of a tetrahedron, equations of lines and planes, laboratory project, putting 3D in perspective. And we'll look at cylinders and quadratic surfaces. Or actually, not quadratic, quadric surfaces. We'll get to that when we get to that video. And then we'll look at a review, and then we'll also do a true or false quiz. And then we'll look at problems plus. All right, so yeah, so these ones are all future videos. Yeah, so stay tuned for that. And this one is the current one that we are working on right now. And then the last video I already did was 3D coordinate systems. So that's it for this particular chapter, vectors and the geometry of space. All right, so let's jump right into the topics to cover. Again, note that timestamps will be included in the video description for each topic listed below. So of vectors, this one we'll go over vectors, combining vectors, definition of vector addition, example 1, definition of scalar multiplication, go over example 2, and we'll look at components, equation 1, example 3, magnitude or length of a vector, vector algebra, and we'll look at example 4. And then we'll do a note on n-dimensional vectors, look at properties of vectors, and then look at standard basis vectors, then go over example 5, then look at unit vectors, example 6, historical note, and then go over applications, and that involves one example, so it's example 7. All right, so now let's finally get to the video. So vectors, the term vector is used by scientists to indicate a quantity such as displacement or velocity or force that has both magnitude and direction. A vector is often represented by an arrow or a directed line segment. The length of the arrow represents the magnitude of the vector, and the arrow points in the direction of the vector. And we denote a vector by printing a letter in boldface, such as this V in bold, or by putting an arrow above the letter, such as V with this arrow on top. And MES note, in my earlier videos, I would bold every equation or symbol since there were no vectors involved, and it's just easier to see those symbols. For this video, I will only bold vectors, just so we don't get confused. So, for instance, suppose a particle moves along a line segment from point A to point B. Yeah, and the corresponding displacement vector V shown in the figure below has initial point A, the tail, and terminal point B, the tip. We indicate this by writing V is equal to AB, so from A to B with an arrow on top, so it's a vector. All right, so let's say you have a point A, and then you have a point all the way to B here. And now you have an arrow going from point A to point B, and this is the vector V. And since it's not easy to bold by writing, I'm just going to put an arrow on top. And I'm also going to add another vector. I'm just going to do the exact same one here. This is going to be from A to B. So let's say we have it instead, we'll go from C all the way, and this is let's say it's exactly the same as this setup. So it's parallel to that, to D. So we have C to D, and we'll call this U with an arrow, so U vector. And now notice that the vector u equals cd over there has the same length and the same direction as v. So same thing, it looks pretty much the same here, same length, same direction, just assume my drawing is accurate, even though it is in a different position. We say that u and v are equivalent or equal, and we write u equals v. So these are the same vectors, they're just moved over or shifted, but they're the same arrow, same magnitude or length, and the same direction. The 0 vector, denoted by 0 in boldface, has length 0. And yes, this is on bold. So this is a length, it's not a vector, it has 0, but the vector is 0 here, has a length 0. So it is the only vector with no specific direction. So you can think of that as a dot and so on. So combining vectors. So suppose a particle moves from A to B, so its displacement is AB and then this arrow line, so that's a vector. Then the particle changes direction and moves from B to C with displacement vector BC as in the figure below. Alright, so let's draw that. So let's say you have a particle here, and it goes from, this is A, and it goes all the way to B, and then it moves over to C. Let's say you have C here. Yeah, so it goes from A, B to now we go all the way to here. And now what I'm going to do is, well, there's another vector we could draw. We can go from A to C, like that. And I'll do that in red. So that's the basically combination of these two. All right, so now the combined effect of these displacements, so again, from A to B, then B to C, is that the particle has moved from A to C. So same thing as just going from A to C. The resulting displacement vector, AC, is called the sum of AB and BC, and we write AC with an arrow, the vector equals to AB, arrow plus BC. So going from here to here is the same as adding these vectors. Again, we're adding vectors, not just numbers. So in general, if we start with vectors u and v, we first move v so that its tail coincides with the tip of u. So, for example, if this is u, this would be the tip of v there. Or in this case, we're starting from u and v, so then v would be over here and tip of u over there. So that its tail coincides with the tip of u, and define the sum of u and v as follows. Alright, so if u and v are vectors positioned so the initial point of v is the terminal point of u, the terminal or end point, then the sum u plus v is the vector from the initial point of u to the terminal point of v. And the definition of vector addition is illustrated in the figure below. So what we'll have is, so here, we'll do this here. So the initial point of v is a terminal point of u. So if we have u is a starting one, and so then v starts at the tip of this one, then the sum, so this one, let's say go like that, and this is v, like that. So that's u and v. So then this means then the vector u, the sum u plus v as a vector is from the initial point of u, so the initial point to the terminal point of v. So it goes like that. So this is the definition of vector addition. Alright, here I just fixed this up, made it a bit neater, and now you can see why this definition is sometimes called the triangle law, because we have a triangle there. So in the figure below, we start with the same vectors u and v, so start there as in the above figure, and draw another copy of v with the same initial point as u. So we'll copy this, then we'll make this one here over to here. So let's start this over. So we have... Alright, so we have u, this goes to u like this. Let's start it actually all the way here. U goes there, then we have v goes there. So let's say the exact same copy there, is a bit smaller, this. And then the next one is, we're gonna go in between here. So this one is u plus v, like that. And now we're gonna draw another v. So copy of v with the same initial point as u. So we'll draw one over here. And here's made it bigger. Just pause video and made it bigger. This is v. And then this means then our u is going to be connected over here. This is going to be our u there. So then this means now we go v plus u is the vector in between. So now we have a u plus v and a v plus u. Those are equal. And now completing the parallelogram, we see that u plus v is equal to v plus u. And this also gives another way to construct the sum. So notice another way is, so you notice the u right here, and there's a v right there, both at the center. And then the one in between there is the u plus v or the v plus u. So another way to construct the sum is if we place u and v so that they start at the same point, in this case right here, then u plus v lies along the diagonal of the parallelogram with u and v as sides. So these are all parallel right here. This is parallel with this, and this one is parallel with this. This is called the parallelogram law. And again, note that a parallelogram is a quadrilateral, which is just a four-sided polygon. Polygon is just any random straight edge shape with parallel opposite sides. So in other words, we'll just make a skewed one. So if you have one like this, and then how would this look? Let's say you have it like this. Yeah, let's say you have it like this. Yeah, and here, yeah, I just fixed it up so it looks like this one here. So yeah, basically you have this parallel, and this one are parallel. So yes, that's a parallelogram. And you can see that these are the vectors there, this vector here. So similar to this setup here. This is more like a rectangle, but nonetheless, rectangle is a parallelogram. All right, so now let's move further or forward and look at example 1. And this one states, draw the sum of the vectors a and b shown in the figure below. So this is what we're given. Now we gotta find the sum, and again, you can just move this over and combine the two. So solution, first we translate b and place its tail, that's the tail right here, at the tip of A, being careful to draw a copy of B that has the same length and direction. Then we draw vectors A plus B starting at the initial point of A and ending at the terminal point of the copy of B. So what we'll do is we'll start off with A. We're going to start off with A right here. And let's draw this exactly like that. It's more horizontal. So there's our A. And now we're going to look at our B. Well, actually, instead of even that, let's see what I can do. I'm going to just copy this. So it's exact. Copy. And let's paste it here. So we're going to copy that. Put it here. This is our A. And now we're going to take this. And we'll just take just B by without the B. Copy. And paste. And we're going to put this exactly right there. So that is our B. And then we have over here, then we draw the vector A plus B starting at the initial point of A and ending at a terminal. So there's their A plus B. A plus B. All right, so that's the triangle law setup, but alternatively we could place B so that it starts where A starts. So instead of putting it at the tip, we could put it right over here and then construct A plus B by the parallelogram law. So what we could do is do the same setup here. I'm just gonna copy and paste both. Copy and then paste it here just so that everything's exact. Move this over. So we start over here. There's our A and there's our B. Okay, this one's like this. And then we're gonna take this, copy this, move it right here. So that is our B. And now we need to construct a parallelogram, so we'll copy this A. So we need to copy the A. I'll do this. And then we need to construct that. This goes right at the tip here. Then we can copy the B. And then paste this. Oops. Oh yeah, fix that up here. Just move it over here. And then move it just like that. It's a bit hard to get it exact. There, all right, so this is our A, this is our B, and in between is, well, right here. This is our A plus B, or B plus A. Yes, so you could write it, let's do it on this side is A plus B, and this side is B plus A, because you go from B, A. This one is A, B. And just to make it a bit neater, I'm going to erase these arrows. And the sign here, just ignore that. This is just parallel. Yeah, here I just erased that and moved it over like that. And now we can have the parallel lines. This one is one line, it's parallel to that. So yes, that is the parallelogram. Let's move this in the center. All right, so let's continue further now. So now let's go over a scalar multiplication. So it is possible to multiply a vector by a real number c. In this context, we call the real number c a scalar to distinguish it from a vector. So there's a real number c is a scalar. There's a vector. This one just has magnitude. This one has a vector has direction and magnitude. So for instance, we want 2v to be the same vector as v plus v, which has the same direction v but is twice as long. So in general, we multiply a vector by a scalar as follows. So definition of scalar multiplication. If c is a scalar, or again, this has to be unbold. Yeah, so if c is a scalar and v is a vector, then the scalar multiple cv is the vector whose length is this c, the absolute value of c, times the length, because this is the length of it, because sometimes you can have a negative, so you could flip it and so on. This is the absolute length there. Yeah, so that's just the length, which is a positive number. So is the absolute value of c times the length of the vector v, and whose direction is the same as v if c is greater than 0, and is opposite to v if c is less than 0. But if c is equal to 0, or v, or the vector v is equal to 0, then c times the vector v is equal to 0. Yeah, equals to 0 as a vector and magnitude. So this definition is illustrated in the figure below. All right, so what I'll do is I'll draw v. Say we have v. From here to here is v. All right, so now if you have 2v, you're going to double that. This is going to be 2v. All you do is extend it double. So that's 2v. And now let's say you have 1/2 v. Well, 1/2 v is going to be half that. So this is going to be 1/2 v. All right, so that's 1/2 v. Just fix that up. And now if you're going to go negative, this is going to be, well, start exactly the same, but go down. This is going to be negative v. And now if you want to go negative but bigger than that, we can go up to here. This could be negative 1.5v, negative 1.5v, like that. Yeah, so this is scalar multiplication. So we see that real numbers work like scaling factors here. And yeah, notice that they're all just scaled up or down in opposite directions or same direction. That's why we call them scalars. So we're just scaling the vector. And now notice that two non-zero vectors are parallel if they are scalar multiples of another. Yes, for example, all of these are just parallel because they're all going in the same parallel direction, either forward or backward. It's still all just a parallel with each other. All right, so in particular, the vector minus v which equals to, let's put this, you could put this as a unbold, but it's the same thing. So a negative v equals to, actually we'll just do it for clarity. So negative v is equal to negative 1 times v has the same length as v, but points in the opposite direction. So notice here, these are parallel. So this v goes up, this one goes backwards there. It's the same length though. So we call it the negative of v. And by the difference u minus v of two vectors, we mean u minus v is just equal to u plus the negative of v. So this negative v there. So we can construct u minus v by first drawing the negative of v. Here, just put the negative of v, and that is a negative v, and then adding it to u by the parallelogram law as in the figure below. All right, so we can draw that here. So let's say we have u, and let's say we have u going like there. There's u. And there is v. So we have v goes like this. This is v. All right, so to construct u minus v, well, we're going to add, it's the same as u plus negative v. So we'll take the negative of this. So we'll go backwards. Like that. Let's start a bit nicer. All right, here, just fix that up. So this is negative v like that. And now we can construct it using parallelogram law. That is basically just construct a parallelogram. So we can construct like this. And like that, and then just combine this straight over there. So this is going to be our u minus v, like that. All right, here, so I just moved it up here and made it a bit neater. So alternatively, since v equals to u minus v, No, I mean, yeah, v plus u minus v is equal to u, because you can just see here. So v plus u minus v, the v's will cancel. We're just left with u. The vector u minus v right here, when added to v, gives u. In other words, if you take this vector v, add this one here over to this part, we're going to get over there. And that is going to get over to u there. So in other words, we can construct this using this triangle law there. I'll just erase all this. All right, so yeah, gives when added to v gives u. So we could construct u minus v as in the figure below by means of the triangle law. So what we'll do is we could draw u here, and then v is here. This is v, and then we'll just go downwards. This is just u minus v. Yeah, so basically instead of adding u on top, we can just subtract it like this. And that is using the triangle law there. Let's move this up. Yes, that's fascinating stuff. All right, so now let's continue further and look at example 2. So if a and b are vectors, are the vectors shown below, so here's a, here's b. Now we're asked to draw a minus 2b. So solution. We first draw the vector negative 2b pointing in the direction opposite to b. So we're going to go here and twice as long. And we place it with its tail at the tip of a. And then use a triangle law to draw a plus negative 2b as in the figure below. All right, so what we'll do is, because again, we're asked to get a minus 2b. So what we'll do is a plus negative 2b instead, because we'll just be adding it up using the triangle law. So we'll draw a. So there's a. I'll just draw it here. So there's our a. It looks something like that. I think it's a bit longer. Let's draw it a bit longer. There's a. Now we're going to look at this b, put it right here, but then do the negative of it and twice as long. So this can be, instead of here, it'll be like that. So this is our negative 2b. And now when you combine these together, you get the triangle law. So this will be a plus negative 2b, which equals to a minus 2b. All right, so now that we've done this, now let's go to the next section. This is on components. So for some purposes, it's best to introduce a coordinate system and treat vectors algebraically. So if we place the initial point of a vector a at the origin of a rectangular coordinate system, then the terminal point of a has coordinates of the form a1, a2, or a1, a2, a3, depending on whether our coordinate system is 2 or 3-dimensional. So see figure below. So let's take a look at over here. So let's say we have a 2D one here. We have x and 0. This is our y. So we have our vector goes like this. This is the vector a. I'll draw this like that. This goes to a1, a2. This is a point right there. And you could also write this as this vector is equal to, if you write this in coordinate form, you could write this with this kind of bracket, this triangle bracket, as opposed to these regular brackets. A1, A2 to indicate it is a vector. So like that. Or you can have it in, let's draw in Z direction there. So that's Z. This is Y. Y is a bit like that. Y. In 3D, so this is going to be our x, like that. So let's say you have a point in space here. This is our A1, A2, and A3, like that. And then there's the origin there, and let's say we have an arrow straight to it. This is our A vector, and this point goes all the way down here. And let's just draw a point from here, drawing it in 3D. So that is what we have. And this one here, and I'll get to this in a bit, you can write this in vector form like this. So if you could write these brackets or these components with this triangle bracket, indicates it is a vector. A2, A3. And here, yeah, I put the arrows on top just so it's clear that this is a vector. And then these ones are all scalar points, but in a vector form. So you write this as a vector like that. And here I usually don't put them here because it's pretty straightforward. These are all vectors, and these are scalars. That's it's pretty straightforward. But here, because we're having the a value already, there's an a there, so just indicate it is a vector there. All right, and yeah, so these coordinates, a1, a2, or a1, a2, a3, are called the components of the vector a, and we write vector a equals to this triangle bracket a1, a2, or in 3D, this a vector is equal to this triangle bracket a1, a2, a3. And we use a notation, these triangle brackets a1, a2, for the ordered pair that refers to a vector, so as not to confuse it with the ordered pair with the regular bracket a1, a2 that refers to a point in the plane. So these refer to this point. This vector, you could write it as this. This is a vector. And this is a point, and this is a vector. So yes. And now, for instance, the vectors in the figure below are all equivalent to the vector, this OP, equals to 3, 2, whose terminal point is the point P3, 2 there. So let's draw a grid here. Well, let's just draw the XY coordinates. So there's the X, and there's the Y. Let's say we have the Y is like this. And now let's draw from OP, so 3, 2. So we go from O, and then this is going to be, let's say it's going to be 1, 2, 3, and then we go 1, 2, so that goes right here, and this is the point P is at 3, 2. So then this is our OP. Yeah, that's our vector. All right, here, let's write this our y, this is our x. So these ones, this is going to be equivalent to if you have the same direction and magnitude, but shifted anywhere else. So if we go from, so the calculus book goes from 1, 3, let's go up 1 here. This point right here is 1, 3. So 1, 3, and then it needs to go up, so it goes right 3 and up 2, so we'll just go up 2, 1, 2. And then we'll go 1, 2, 3. So another one there. So that's going to be right here. So this is the same point right here. This is at 4, and we're going up. So this is 2. So go 1, 2, 3 there is going to be at 5, 4, 5, like that. Let's draw this point right here. And now another arrow that calculus book drew goes from 2 and then dash 1 here. And then this would go, well, again, 1, 2, and then 1, 2, and then another 3 here. This will be right here. So this is the equivalent to the center one there. All right, and there's 3 more the calculus book drew in, just for completeness, let's get them all. So it goes 1, 2, and then 3, and it goes up 1 here. And so that is 1, then we go again. So we go 1, 2, 3, and 1, 2. So we go all the way up here. Like that. And then another one goes to -2 and then 1. Here's the end point. So that means we have to go 1, 2, 3. Then we got to go down 2, 1, 2. So that this goes all the way across right here. And there is an arrow. And then just one more. It goes. This is the end point right here. So it goes 1, -2 at the bottom. And then we go 1. Let's make this a center here. Goes 1, 2, 3, and then goes 1, 2. So 1 here. Draw this here, and goes all the way across like that. Yeah, so anyways, just wanted to exercise in plotting. So all these are equivalent to this one here. That's our OP from the origin to the point P. So those are all equivalent vectors. All right, so let's continue further. So yeah, so what all these have in common, so what they have in common is that the terminal point is reached from the initial point by a displacement of 3 units to the right. So yeah, we go here 1, 2, 3, and then and 2 upwards. So we go 1, 2. So every single one is 3 right, 2 up. So we could think of these geometric. We can think of all these geometric vectors as representations of the algebraic vector A equals to 3, 2 there, these triangle brackets. And the particular representation OP from the origin to the point P, 3, 2 is called the position vector of the point P. So we could write this as OP P, like that. And yeah, so now in 3 dimensions, the vector A equals to, which OP with arrow on top is this notation of the vector, is equal to, yeah, the triangle bracket A1, A2, A3, and this one right here from 0 to P is the position vector of the point P, which has coordinates A1, A2, A3, and so on. So see figure below. So this is in 2 dimensions. There's the position vector of this point right there. And again, position vector is from the origin to the point. So now if we draw this out in 3D, so if we have it in 3D, this is our Z, and this is our Y, like this. And now we're going to move this, yes, made it a bit shorter, and let's draw the Y. Y is like this. Then draw the X. X is like that. And let's get the point here. So let's say we have a point here. I'll just make it a bit more horizontal. So there's our point P, like this. P, and yeah, here I quickly shifted everything up more, made this more horizontal, just to match my calculus book. So this is the point P right here. So if this is the point P, its position vector is going to be the vector from the origin. Let's draw this origin here. Or better yet, let's just draw point P. This one has coordinates A1, A2, A3, like that. And now it has, this is from the origin all the way into this point P. This is going to be the position vector of P, and this is right over here. Make this capital P. Alright, so now that we have this, and now what we'll do is, well, let's take this further. So let's consider any other representation, we'll call that from A to B, of this A, where it has a position vector OP. So from 0 to P, it's over here, but we'll just take this exact same vector, but move it anywhere else. So where the initial point is A, and then has coordinates x1, y1, z1, and the terminal point is B, x2, y2. Z2. So let's say we start off instead, we'll go up to this point A. So we have this point A. This has x1, y1. This is going to be our z1. And now we're going to want this exact one right here. So this is OP, like that. But again, this is just our vector A in OP form, in position vector form. So we're going to have now, instead of OP, we're going to go from A to P. And this one's going to go all the way up to the exact same parallel there. This is going to be up to this point P. I mean, up to point B. That is our point B, and it has coordinates x2, y2, z2, like that. And this is our A is equal to this representation, A to B vector. All right, so now if this is this vector right here, AB, is equal to this A vector, the same as exactly this one here, if there's just different representations of the same exact vector, then we must have these coordinates has to be, well, just this one here added by these exact coordinates here. So you're moving exactly the same displacement there. So thus we must have x1 plus a1 equals to x2. And also, we have to have y1 plus a2. So we have to go, this a2 has to add with this one, has to equal to this. And so on, this equals 2x, this is going to be y2. And then likewise, we must have z1 plus a3 has to equal to z2. So in other words, this right here has to be equal to B, and this is going to be x1 plus a1. And then the y2 has to be y1 plus a2. And one more, actually. And then last one, z1 plus a3, like that. And now what this all means is, well, we could just take this over and move it to the other side. Same thing with here, y, move it to the other side. Z, move it to the other side. So we subtract x1 from x2 and so on. So we get, this whole thing becomes a1 is equal to x2 minus x1. and then a2 is equal to y2 minus y1. So we could solve for these differences right there. And then a3 is equal to z2 minus z1, like that. So we just write them all like this, and this just becomes the position vector here, because a1 minus 0, these are all the origin is going to be a1. a2 minus 0 is a2. And then a3 minus 0 is a3, and so on. So we could look at this and see all the differences there. So we get this, which is a fascinating result. So we could take the difference between any 2 points and find its position vector. Alright, yeah, so this is pretty fascinating stuff. So yeah, you could just take these A points and then take the difference. It just equals to the difference between any 2 points that have the exact same vector, same direction and length. So thus we have the following result, and we'll call this equation 1. So given the points A, which has coordinates x1, y1, z1, and B with coordinates x2, y2, z2, the vector A with representation A to B is, you can just write this as the vector A equals 2, and then in vector form, write this square bracket, this triangle bracket, x2 minus x1, y2 minus y1, and then the third component is z2 minus z1, which is quite a fascinating result. Alright, so now let's take a look at an example. So example 3. So this one states, find the vector represented by the directed line segment with initial point A, 2, -3, and 4, so the coordinates 2, -3, 4, and the terminal point B, which the coordinates has -2, 1, 1. So let's look at the solution. So by equation 1, so this one right here, the vector corresponding to AB, this equals 2, and here we'll just write this as A, let's call this vector A, this equals 2, AB, and this just equals 2, and in vector form, so we're going to have the difference. So it goes from B minus A. So we'll go -2 minus 2, -2 minus 2, and then we'll get 1, this is our y2, minus y1. So we'll have 1 minus -3, and then we'll have it, yes, and then the last one here, we'll have z2 minus z1, so 1 minus 4, so 1 minus 4, like that. So this would equal to -4, and then 1 minus -3, that's 1 plus 3, that becomes 4. Negatives become positive, and then the last one, 1 minus 4 is equal to -3, like that. So yes, this is our vector, like that. Alright, so now let's continue further. Now let's take a look at magnitude or length of a vector. So the magnitude or length of the vector is the length of any of its representations and is denoted by the symbol. You can have this vertical line, then the vector form right here, so vector V, then closed line there. Or you can have double lines and then V and then double lines. Yeah, I typically see this one. Here's the one I use more. Also because this one, I can't really find this on my keyboard. It was by using the distance formula to compute the length of a segment OP, and we obtained the following formulas, and again I'll just put a note. This is from the first video in the in this chapter. Yeah, so from that first video I went over the proofs for the 3-dimensional one and also 2-dimensional, and so on. So the length of the 2-dimensional vector A equals to, this vector A, its components A1, A2 is, and this is just using the Pythagorean law. So we'll have the absolute value of A, the vector, is equals to square root A1 squared plus A2 squared. So you just square the components, add them up, and then square root the whole thing. That is in 2 dimensions, like that. And now in 3 dimensions, so the length of the 3-dimensional vector A with components A1, A2, A3 is, and again, the same thing, but you just expand this. So A vector equals to the absolute value of it, or the length, is going to be equals to A1 squared plus A2 squared plus A3 squared. All right, so now let's move further. Now we'll take a look at vector algebra. So the question is, how do we add vectors algebraically? So the figure below shows that if A has components A1, A2, and B has components B1, B2, then the sum is A plus B equals 2, and then you just add the components A1 plus B1, A2 plus B2, at least for the case where the components are positive. So let's take a look at geometrically. So we have, I'll write this like here, there's our y, there's our x, so x and y, there's the origin. And now let's take a look at where a, let's say we have the vector a, and this vector a goes over here. And yeah, I'll just move it over here. So this is the vector a, and it has components right here. I'll just draw this dashed line, like that, A2, and then this is A1. All right, so now we have this A vector. Now let's take a look at the vector B, and it has components of B1, B2. And yeah, remember this B1, B2, these are just the position vectors of it, and they're the same as the difference between any 2 points for other representations. So this one right here, A1, A2, it's equals over to here. Yeah, right here, when you take the difference, you subtract these out, you're just left with A1, A2. So in other words, we can put it like this. Let's say we have B that looks like this. Make it pretty big like that, just so we can have more space. So let's say we have B goes all the way up to here. This is the vector B right here. And I'll just put this B with an arrow on top. All right, and now this has components, and we got to be careful on this. So this component, this has to start from the base of the vector to the terminal end. So in other words, this is the base. So then from here to the end, this one has coordinates or components B1, and then this component from here to here, this is our B2, like that. Yeah, so let's put it like that. I'll just put the here, so just so we know it's from here to here is, yeah, it's from here to here is B2, like that. Whoops. And now we're going to draw the combination vector. So we're going to add A plus B, and we're going to show that it's equal to, well, A1 plus B1, A2 plus B2. We're going to draw this all the way across like that. Like that. This is going to be our, like that. This is going to be our A plus B vector. And now you can see the coordinates right here. This one is just, well, from here to here. Let's go from, let's go like that. From here all the way to, yeah, from here to here. This is just our A1 plus B1. Right here, just fix it up. So A1 plus B1, and then this from here to here, this top or to the bottom, that's just A2 plus B2. So A2 plus B2. So in other words, this point right here, is going to be A1. Let's put an arrow, or just put it like this. So this point right here is going to be A1 plus B1. That's the coordinates, and then this is going to be A2 plus B2. So yes, exactly as shown over here. Yeah, so you just sum that up algebraically. Yeah, so in other words, to add algebraic vectors, we add their components. We just add them up like that. Similarly, to subtract vectors, we subtract components. And yeah, the calculus book didn't draw this out for the subtraction, but I'll just do that here. All right, so let's go with our exact same setup above. And now we're going to go like this. This is our x, this is our y, there's our origin. We'll go A first. Let's say A is like this. There's the there's a setup, or actually let's make it bigger, just because we're going to be subtracting, so it's going to be more convoluted. So this is going to be A, like that, has components. The components are this is A2, and there's A1, like that. All right, so now to subtract a vector, well, that just means adding a negative vector. So in other words, we can just write this, let's say we have a vector like here, goes all the way across here, and we'll call this a B vector. It has components let's draw these as positive. This is going to be B2 is the vertical, and there's the B1 is the horizontal, like that. Now if we take the negative of it, well, that's going to go all the way down, and this is going to have components. There's going to be negative B1, so it's a negative vertical one, and then we're going to have to draw a full-on like this. I'll just do this here. Dash line like this. And this is going to be all the way here. This is going to be our negative B2, so it's a negative of it. And yeah, just extend this over like that. All right. So then just to point it out that this whole negative B2 is at the bottom there. And now this is going to be, yeah, the negative B vector. Write a better B. And now from here to here, this is going to be, well, A plus, because we go from the tip, so tip there, so we're going to plus negative B vector. And now this just equals to A vector minus B vector, like that. And now this coordinates right here, this point right here, this is just equal to, yeah, here, just move this over to here. And then, yeah, so this point's going to be, well, just going to be A1 minus B1. And then the second one is going to be A2 minus B2. And you can see this here, yeah, because this horizontal distance from here to here, which is going to be the horizontal component, this one right here is equal to, well, A1 plus negative B1. So in other words, this is just going to be A1 plus negative B1, and then those just become negative. You just see that already. So B1, like that. So we take this part all the way from here to here, subtract this out, becomes this. Now the vertical component from here to here, this part right here, let's draw it like this. This is going to be, well, A2, and then plus this negative B2. In other words, A2 minus B2. And then what we'll do is we'll take this segment, we'll take this top one, and then subtract by this top one, this bigger one here, and you just get this negative side over there. So yes, that is this part right here. So we just subtract the components. Yeah, exactly the same as this one here. So add and then add and subtract the same thing, but you're adding the negative side. All right, and now if we look at scalar, so from the similar triangles in the figure below, we see that the components of C, which is scalar times by A, the vector, are just CA1 and CA2. So what we'll see is, let's just draw this out right here. So if we have this vector, we'll call this A vector. It has components of like this, and the components are A2 is a vertical, A1 is that. And now let's make the exact same one, but a similar triangle. I'm just going to take this exact same line, just copy and paste it. It says exact same one. Move it over to here, and let's just expand this out in the exact same line. So the angle's exactly the same. So we're shifting this over, and the similar triangles here, this is going to be an angle like that, theta. When you're shifting it, this is just going to be scaling this bottom part, CA1. So it's the same exact angle. So if it's the same angle, the ratios have to be the same. The only way the ratios can be the same is if there's the constant C right there. And this is a CA2. So in other words, the components are just multiplied there. And notice the ratio A2 over A1 is equal to, let's put this here. Yeah, A2 over A1 is equal to CA2 over CA1, and these cancel. So it has to have the exact same one, right angle, like that. And then this is the vector, and this is going to be C. So remember, when it's components, all you're doing is changing the components by just scaling that up. You're just scaling the vector up. Because remember, the vector just points to that point there, and that point's going to be the CA1 times, and the CA1 is the horizontal, and the vertical CA2. And yes, so that is what we have. All right, so to multiply a vector by a scalar, so vector by a scalar, we multiply each component by that scalar. So multiply these each other, it just means you're multiplying the components. So if the vector A has components A1 and A2, and the vector B has components B1, B2, then A plus B is just equal to the components added to each other, A1 plus B1. and a2 plus b2. And then subtraction, we just subtract the components. And then the scalar, we just put the scalar, multiply the components by that scalar. Similarly, for three-dimensional vectors, we have this a1. So this vector right here with components a1, a2, a3. Another one b1, b2, b3. We just add all the components. And likewise, subtract all the components. And likewise, we can multiply this by scalar, all the components. It's fascinating stuff. All right, let's continue further. Now let's take a look at example 4. So if we're given that the vector A has components 4, 0, 3, and the vector B has components -2, 1, and 5, we're asked to find the length of the vector A and the vectors A plus B, A minus B, and 3 times B, and 2A plus 5B. All right, now let's take a look at the solution. So the length of the vector A, well, we just know that from our Pythagoras. This just equals 2, well, the square root of the components squared and added up of the sum of the squares of the components. So this is going to be 4 squared plus 0 squared plus 3 squared. This equals 2. Well, 4 squared is equal to 16. 0 squared is 0. 3 squared is 9. And 9 plus 16, that is 25. And then square root 25, this equals 2, well, 5. And yeah, we're ignoring negative here because square root 25 could be plus or minus 5 there. Yeah, I'll state that just because it's an interesting tidbit. So we have 5 is our answer for the length here. Now we're asked the vectors A plus B. So A vector plus B vector equals 2. Yeah, equals 2. Let's just write these out, and then we're going to combine all of the components. So this is 4, 0, 3, and then this is going to be, the next one is plus, the B1 is over here, -2, and then 1, and then 5. Yeah, now we just add the components. This equals 2, 4 plus, so 4 plus -2. And then we'll have 0 plus 1. Then we'll have 3 plus 5. Like that. And now this equals 2. 4, yeah, so 4 plus -1 is just 4 minus, plus -2 is 4 minus 2 is 2. Next one is 0 plus 1 is 1. 3 plus 5 is 8. Like that. So that is our A plus B. So we're solved this one. All right, so now the next one is subtracting. So A minus B. So A vector minus B vector equals 2. So let's write this out for completeness. 4, 0, 3, the components of the first one of A. Like that, make this better, 0. Minus, now we'll have a -2, 1, 5, like that. And again, this equals 2. This equals 2. This is going to be 4. Instead of plus, we'll go minus now. Minus -2. And then we're going to get a 0 minus 1. Then we're going to get 3 minus 5, like that. Now this equals 2. So 4 minus -2 is going to be 4 plus 2, which is 6. So 2 negatives become a positive. So this is a 6. And then we'll have 0 minus 1 is, well, just -1. And then the last one is 3 minus 5 is -2. Like that. So yes, now we can box this in. And now the next one, that is going to be, well, this 3 times B. So 3 times B is just going to be, well, 3 scalar times by B vector. This equals 2. And the B1 is just -2, 1, 5. So this equals 2, 3 times it by, and then we'll have the vector form, the components -2, 1, 5. And now this equals to multiply that inside each one. So this becomes, this is going to be 3 times -2, 3 times 1, and then 3 times 5, like that. And now this equals to, well, 3 times -2 is -6. And then, or actually what I'll do is, I'm going to write this down here. This equals to 3, -6. And then the next one, 3 times 1 is 3. And the next one is 3 times 5 is 15. Like that. So we have negative 6, 3, and 15 as the components of 3 times b. All right, and now I think the last one, yeah, so 2a plus 5b. So we'll write 2a, yeah, so 2a plus 5 times by the vector b. So again, 4, 0, 3, negative 2, 1, negative 2, 1, 5. All right, so this equals to 2 times, let's for completeness write this out, so 4, 0, 3, and then plus 5 times negative 2, 1, 5, like that. Negative 2, 1, 5. All right. Multiply this inside. This is going to be, well, 2 times 4. Or instead of just writing that, calculus book just skips it all, just writes it straight up. So 2 times 4 is 8. 2 times 0 is 0. 3 times 2 or 2 times 3 is 6. And now plus, and now we do over here. So 5 times negative 2, that is negative 10. Next one, 5 times 1 is 5. Next one, 5 times 5 is 25, like that. And now we're going to have to add the components. So this equals 2. So this equals 2, and just do this all in one go. So 8 minus 10 is equal to negative 2, like that. The next one is 0 plus 5 is 5. Next one is 6 plus 25, that's 31. Yes, that is what we get. All right, so now let's go further, and now we denote by v then subscript 2, or v sub 2, the set of all two-dimensional vectors. And yeah, basically all two-dimensional vectors, we'll just say it's all inside this set here. We'll call this v2. And by v3, the set of all three-dimensional vectors. So more generally, we will later need to consider the set Vn of all n-dimensional vectors. Yes, instead of two-dimensional or three, Vn is just all of them. An n-dimensional vector is an ordered n tuple, right? Yeah, instead of a triple or double, you got a tuple. This is an n amount. And you could write this vector as a's, bolt a equals 2, and then the components a1, a2, all the way to an, where a1, a2, and an are real numbers that are called the components of a. And addition and scalar multiplication are redefined in terms of components, just as for the case n equals to 2 and n equals to 3. So yes, yeah, the definitions still hold as for case n and case 3, and you could go any number of components, and this the definitions still hold, the addition and scalar multiplication and so on. And continue further. So now just a note on n-dimensional vectors. So vectors in n dimensions are used to list various quantities in an organized way. For instance, the components of a 6-dimensional vector, so you have, let's say, a vector p equals the components p1, p2, p3, p4, p5, and p6, might represent the prices of 6 different ingredients required to make a product. So in this case, this set would be for all the prices for a specific, for a specific product with ingredients, so prices of ingredients, and so on. And 4-dimensional vectors, x, y, z, and t, are used in relativity theory, where the first 3 components specify a position in space, so x, y, z, and the 4th represents time. So yes, you can go, you can have different dimensions and so on. Yeah, and then use n-dimensional vectors to describe them. That's very interesting. So now let's continue further. All right, yeah, so these are some properties that some of them we already covered earlier of vectors, and some basically we'll go over in a bit. So basically, if A, B, and C are vectors in a Vn, so the set of all n-dimensional vectors, and C and D are scalars, then you'll have these properties. So property 1 is A plus B equals B plus A, so we've already covered that. And then this one here is A plus B plus C is equal to A plus B, and then plus C, so the order doesn't matter there. And then you'll have A plus 0 is just A, because this is a 0 vector there. And then a plus negative a equals to 0. So you're adding the negative of it, and this goes back to itself. And then c is, this is the property 5. Scalar c times the vectors a plus b is equal to, and you can multiply this scalar inside. So ca plus cb. And likewise, we have c plus d scalars times by a. You can multiply the vector inside, so you'll have ca times, plus d times vector a. And likewise, we have c times d times by cd times the vector a. You could take out a scalar, so you could take out c, or you can take out d, and then you'll have it c, for example, times d times a. So the order doesn't matter there. And also a scalar of 1 times a, the vector, is just equal to a itself. And now, these 8 properties of vectors can be readily verified either geometrically or algebraically. For instance, property 1, this one here, a plus b equals to b plus a, so you can just switch the order, can be seen from the earlier figure for the parallelogram, or as follows for the case n equals 2. Well, let's go up to the parallelogram, parallelogram rule first. All right, here, I just teleported above here. So here's the parallelogram law. And and you can see here, so if you go u plus v, you get this u plus v, or you can go v plus u, you get the exact same thing. So v plus u, it's the same vector there. So now if we do this algebraically, let's just also verify it here. Scroll down here, and we should be here. All right, there we are. All right, so let's write this out. So for the case n equals 2, so if we have the vectors a plus b, so again, try to match this here, and we got to make it equal to b plus a. Well, in components form, this equals to a1, a2 plus, and then this is going to be b1, b2. And then we've already defined that vector addition. You could add the components. So this is going to be a1 plus b1, and then this is going to be a2 plus b2. And now what we could do is, well, we could just move these around. When you're adding real numbers, you can go back and forth. We could just switch these around. So this equals to b1 plus a1. And the next one is b2 plus a2. And this just equals 2. And now we could, take out these components. Because so vector addition is just adding the components. So in other words, this we can get just separate out into the earlier components. This is going to be, it's going to be actually, first this is a comma, not a other bracket. So we have this, so b1 plus a1, and then b2 plus a2. Yeah, so and now we could separate these back into how we started over here, into 2 vectors. So this is going to be just b1, b1, and then b2. So b1, b2. So we just switched the order, and this is going to be plus. And this is going to be now the next one, a1, a2, like that. Yeah, so now basically we first went from this part right here and then added the components, and then we switched the components and we went separated back over to this side, but we have the b in front now because we've switched these around. And now write these in the vectors in the vector form. This just equals to b with the arrow, so b vector plus a vector. So yes, this is just verified. So a plus b vectors equals to b plus a, like that. So a there, and circle this. All right, and now the next property we could take a look at is property 2. So we can see why property 2, the associative law, or the associative law, you can see that right here. So a plus, then bracket b plus c is equal to a plus b, when you do this first in the bracket, plus c, like that. And as associative, you could just basically associate either or. So you could associate a plus b in this one, or b plus c here first, and then add to the other term or other vector. So we could see why the property 2, the associative law, is true by looking at the figure below and applying the triangle law several times. And basically, he'll read this first, and then I'll draw it out. So the vector PQ is obtained either by first constructing a plus b, and then adding c, or by adding a to the vector b plus c. So do that either or. Yeah, so let's do this one here. Let's say we have a point here. We'll call this P. And let's say we have the point Q over here. So we want to get over to this PQ vector. So that's PQ vector. And we want to construct that in two ways. Well, let's go to the first one. Let's say you have A. The A is this. So that's A. And then let's say you have right here, B. So B goes over there. Or even better, I'll make it a bit shorter. So let's say this is B. So that's B. So this means then this is A plus B. So we have A plus B. I'll put a bracket just so we can understand that which ones we're doing first. So let's say we have A plus B. Is this just using triangle law? Just add them up like that. All right, here, just fix that up. So we have A plus B there. And in other words, we have this right here. So we have A plus B. Yeah, put that bracket again. All right, so we have the bracket there, and then we're going to add C now. So C would be, well, we need to get to Q. So C is going to be, let's say there's a vector here. Now we're going to apply the triangle law again. This is going to be C. So in other words, yes, C like that. Yeah, so in other words, PQ is equal to, we're going to have A plus B, put a bracket, and then plus C, like that. Yeah, because we have this A plus B plus C, and then that's just this PQ. Or what we could do is, well, let's move this over, because we're going to draw it through it. So let's say this is, I'll just make this here. So this is going to be our A plus B. So we could do it that way, or instead of that, what we could do is we can start off at A here. So A plus, and then, well, this one right here. So if we go B plus C is going to be this right here. So this, put this in red. This is going to be our B plus C. So just using triangle law. So go here, there to the tip. So that's B plus C. Or I could probably just write it here, actually. B plus C, like that. Yeah, so we have B plus C there, so erase this part here. So now what we have is, well, we have this B plus C there, and this goes to Q, so we could just start off with, well, A plus this vector, B plus C, and we end up over to here, which is our exact setup. So we're going to have that, or, we'll just put this in red, actually, equals to A. Yeah, we'll still have this PQ, just like that. So it's the same thing. PQ is either A plus B plus C, or just erase this, is the same thing, equals to A. So we're going to construct this triangle law A plus this bracket there. B plus C. So there's the associative law, or property 2. And now we just box these in. So this one, or box this in. And that's property 2, so that matches exactly here. So A plus bracket B plus C, or A plus B plus C. It's both equal to each other. Yeah, so those are these properties 1 and 2, and the other ones are pretty straightforward. Here is adding a 0 vector. This is a negative one. We already went over that. This is multiplying C inside, just the constants inside. And you can multiply, if you have constants added, you could separate that and just add multiply the vector inside each one and add them up and so on. These ones are all pretty straightforward, even this, especially this 1 times A, that's just A. All right, so let's just continue further and now look at standard basis vectors. So 3 vectors in the set of 3-dimensional vectors of V3 play a special role. So let I, the vector, equals to and has components 1, 0, 0, and then J have components 0, 1, 0, and then K have components 0, 0, 1. And these vectors, I, J, and K, are called the standard basis vectors. So they have length 1, and point in the direction of the positive x, positive y, and positive z axes. Similarly, in 2 dimensions, we define I, vector I equals to, has components 1 and 0, and then J has components 0 and 1. And here I'm going to draw this out how this looks like, and draw this in 2D and 3D. So if you have in 2D, so here's standard basis vectors. Let's say you have the x, and that's the y, and this is the origin. So now this would mean that we're going to have a vector. Let's say at this point right here, say this is at this point is 0, 1. So that's 0, 1. And this point is at x is 1 and y is 0. Yeah, so then in the horizontal one's going to be I. This one's going to be j. And I'm going to draw this in red. Yeah, so let's draw the vector there in red. So this goes there. And this one right here goes like that. Alright, yeah, so that is in 2 dimensions. And now if we draw in 3 dimensions, it's going to look something like this. Let's draw this is going to be our our x. Like that is our x. There is our z. And there is our y. So that's our y, like that. So now what this means is we're going to have a I, it's going to be out here for the x. J is over here for the y. Make this higher. And then this is going to be our k right there. All right, and now here I'll draw this in red. It's going to be like that. This one is here for this. So the k is the vertical. The j is the y, and then there's the I is the this x one. And for completeness, let's just write the point right here. So at this point right here, that point is going to be at 0, 0, 1. This one here is the y. This one is going to be 0, 1, 0. And then at this point right here, this point is going to be, oops, better arrow. Do one more time. All right, here, that's the arrow. So that's going to be 1, 0, 0. 0 and 0. All right, so now that we have these figures right here to illustrate the standard basis vectors, so now if the vector A has components A1, A2, A3, then we could write these using this notation, which is comes in handy in a lot of applications. So let's say we have a vector, put the arrow on top, equals to the components A1, A2, and A3. This means then this equals 2, and what we could do is, well, we could write these as a summation of a bunch of vectors. I'm going to put this A1, 0, 0, so that we get rid of all the other ones. We're going to get 3 vectors here, and it's going to be A2, 0, 0. And this plus is going to be A3. Actually, no, this is not A2 there. This is 0. This is A2. So we just take away the zeros besides the A1, A2, A3 in their corresponding vector, separate vector there. It's going to be 0, 0, A3, like that. And now what we'll do is, well, factor out the A's, just using just basic properties. These are just scalars or real numbers. We're going to get 0 and 1, 0, 0. Plus this A2, factor it out, 0, 0, or not the 0, there's 1 there. And then 0. The next one's going to be A3, 0, 0, 1. Like that. And now this equals 2. Well, those are just our standard basis vectors. So that's just going to be our I, j, and k. Those are I, j, and k. So these ones are I, j, and k. So in other words, we could write this vector A with components A1, A2, A3 in expanded basis vector form as A1 times by I, the vector, and then plus A2 times it by j, the vector, and then plus A3 k, the vector, arrow on top. All right, so we have that. I just fixed it up, and I'm going to put an arrow here, and I'm going to put this A vector, and I'm going to box this whole thing because this is an important equation. Oops, let's keep going. Box it out. Yeah, so thus, what we have is, well, thus any vector in the set of 3-dimensional vectors, V3, can be expressed in terms of the standard basis vectors. So I, j, and k. So for instance, this number, or this vector 1, negative 2, 6, with the components that you could just write that as I minus 2j plus 6k. And similarly, in 2 dimensions, we can write the vector A with components a1, a2 is equal to a1 times by I plus a2 times by j. And now see the figure below for the geometric interpretation for the above equations. Well, this one here and this one here. All right, yeah, so I'll just keep this box. So we have this one 3D, this one 2D. So now we'll see the figure below for the geometric interpretation for the above equations and compare with the earlier figures for the standard basis vectors. We'll compare with these ones right here. So if we look at this one here, these are all just squares. This is all the same length, length 1, and so on. But now what we're going to do is, well, this is the same thing, but we're scaling each one of those. And then we're going to draw a vector that touches that point. So what we have is in 2D, we're going to have like this. I'll just draw this a bit bigger. So this is 2D. All right, so this is 2D. This is Y. This is our X. This is our 0. And now what we have is, so this is going to be our 2D, so a1i and then plus a2j. So the length is going to be, we're going to have two vectors here. So this is going to be, well, I'm going to draw this arrow like this in here, just because it's on there. Yeah, so for the basis vectors, this is going to go there, and this one's going to go somewhere here. All right, here, so that's in red, and now I'm just going to write this in regular black. This is going to be our, right here is going to be our a1 times by I vector. And now this right here is going to be our a2 times by our j basis vector. So basically you're just scaling those up, and then we go up here. This is going to be just our a, like that. Yeah, so basically you could write this vector a and this components here. This is going to be a1 times by the I standard basis vector, and then a plus this other vector a2 times j. And now that's in 2D. Let's take a look at 3D. But first let's compare this one here. So if you look at this one here and here, this one is just here, but now we're gonna scale this I and j by a1 and a2 and move this over to here so we get added and so on. This was just quite fascinating. Now in the three-dimensional case, we're gonna have a z like this. And then we're going to have a z like this. Let's make it a bit more compact and even less push. So this is our x, that's our z. And this is our y, like that. Let's make this a bit further. All right, here now I'll just draw the a first. So let's say we have our a goes all the way up to here. This is our a vector. All right, so now here, actually before we get to that, I'm going to draw this point right here. This point is at a1, a1, a2. Like that. And then this point right here is going to be at, this one's going to be at a1, a2, a3, like that. All right, so now let's draw, draw the basis vectors in red. So first we're going to have to go from this part right here. Actually, let's just draw this out like here. This is going to go somewhere like this. Let's say it goes all the way to here. So this is the vertical one. This is the y one. And that's a vertical one. There's the y version. And this is the x-axis one. All right. This is going to be our a1i vector. This is going to be our a2j vector, and this is going to be our a3k vector, like that. And again, if you compare this with the earlier figure, this one here just goes to this figure is just showing you the basis vectors, all starting from the origin, and notice how they're all just 1 unit length here. And if you were to add these up, you're just gonna get a unit Actually, longer than unit 1. You'll have probably square root 2 length distance here, because using the Pythagoras theorem. There, it's going to point there, and this would be 1, 1. This should be square root 2, but it's in 3 dimensionals, so that's going to be actually bigger than that. Square root 3, actually. Because it's going to be 1 squared plus 1 squared plus 1 squared, and that is just, square root 3. Which will be the 3-dimensional setup here, like that. And here, just fix it up. Yes, it's a 3-dimensional setup, actually, like that. Alright, anyways. So that is how it looks like, but now notice that they all just get scaled up. So you scale up the basis vectors and so on, and you put them at the tip of each arrow, and then you're gonna get your vector in 3D like that. Pretty fascinating stuff. And lastly, for completeness, I'm just gonna write this here. So this is in 2D. This is gonna be a vector equals to, this is gonna be a1i plus a2j vector. And this one here is a is equal to a1i vector plus a2j vector plus a 3k vector. Alright, so now that we have this, let's continue further and now look at example 5. So if the vector A equals to I plus 2j minus 3k, and the vector B equals to 4i plus 7k, then we're asked to express the vector 2a plus 3b in terms of I, j, and k. Alright, and now let's take a look at the solution. So using properties 1, 2, 5, 6, and 7 of vectors, we have, and this is from my calculus book there. So 1, 2, 5, and 7. Let's see what those were. So this one here is a basic 1, 2, and then 5. So 1, 2, 5. This one here, multiply this constant inside. 6 and 7, basically just different ways of combining with these scalars there. Scalar multiplied inside the addition of the vectors, or you could factor this out and go, you could factor out a vector out and so on. You can multiply this in different ways. Alright, so anyways, let's just go over it because it's pretty straightforward vector algebra. So we want to get 2a plus 3b in terms of I, j, and k. And notice this one here the b one has no j. In other words, that's just 0 times j. So in other words, we have 2a plus 3b equals 2, and now I'll just write this whole thing out. Or we're going to do actually multiply 2 times it by, we're going to have the I plus 2j minus 3k, and then put this bracket, and I'm going to put plus. Now we're going to have, 3 times the b vector. So 3 times it by b is the 4i plus 7k. What I'm going to do is I'm going to put the j there too. So plus 0 is the times by j, and then plus 7k, like that. I just put that there just for completeness there. You can ignore it or not. It doesn't matter. I just want to put that there for reference. So now if we multiply this inside, and this is using which property is that? That is, let's go to the property. To multiply this one inside. That's just going to be this property that we're using there. And so on. It's just fascinating. Alright, so 2i vector plus 2 times 2 is 4j vector minus 6k vector. Then plus here, multiply this inside, 12i vector, and this one, that's just 0. We could, let's just ignore that. So it's 0. Then this next one is going to be 3 times 7k. 7 is 21. So 21k vector, like that. And now if we combine all the like terms, so this one is 2i plus 12i. That again, using that property, let's see which property is that. That is this factor one there. So this one here, then we could take out the constants and add those up. That's fascinating stuff. All right, so take that out, factor out the I. This becomes 14i vector Yeah, 14I vector. The next one, 4j. The other one's a 0, so that's just going to be plus 4j plus 4j vector. And now the next one is k. So the k is 21 minus 6 is going to be plus 15k, like that. And now I'm going to box this out. So yeah, that is our combination here. 2a plus 3b equals to this right here. 14i plus 4j plus 15k. All right, and now let's go further, and now let's do a historical note. In the topics to cover, I had this a bit later, but I think it's better fitting to do this now. So historical note. This is Josiah Willard Gibbs, 1150 February 1839 is when he's born, and died April 28, 1903. As a professor of mathematical physics at Yale College, published the first book on vectors, called Vector Analysis, in 1881. More complicated objects called quaternions, I might go over this in a future video, had early been invented by William Roman Hamilton. He was born either the 3rd or 4th of August, 1805, and died the 2nd of September, 1865, as mathematical tools for describing space, but they weren't easy for scientists to use. So these quaternions weren't easy to use, and quaternions have a scalar part and a vector part, and are generally written in the form a, the scalar, plus b times I, the vector, plus c times j, plus d, k, and k, where a, b, c, and d are real numbers, and I, j, and k are the basic quaternions. So notice there's a separate scalar by itself without the vector, so that's the interesting part. So Gibbs' idea was to use the vector part separately, hence he has that ijk, right here, but I think these are a bit different. So anyways, Gibbs was using it separately, and James Clerk Maxwell, he was born the 13th of June, 1831, died the 5th of November, 1879, and Oliver Heaviside, born 18th of May, 1850, died the 3rd of February, 1925, had similar ideas, but Gibbs' approach has proved to be the most convenient way to study space. So just using the vectors separately as opposed to using this scalar there as well. And this is a historical note, and this is an interesting topic on its own. So anyways, continue further and look at unit vectors. So a unit vector is a vector whose length is 1. For instance, I, j, and k are all unit vectors. And in general, if the vector a is not equal to the 0 vector, then the unit vector has the same direction as a is. Yeah, but the 0 vector has no direction, it's just a point in space. All right, so I'm going to write this out. So it has the length of 1. So in other words, if you have a unit vector u for a vector a, so let's say you have, so the vector a, you're going to multiply, or you're going to divide this by, because you're going to scale it down by the length of that vector. So 1 over the distance of the length of the vector a times it by the vector a. So you're going to scale this down, so you're dividing it by its own length, so that it becomes a length of 1. Like that. So in other words, this equals to the vector a over the length of the vector. And here we could draw this out. So calculus book doesn't do this drawing, but I think it's pretty useful to do. So this is the just u. Keep that in mind. So u. So basically, we scale this vector. So you have it in x, y. Move it here. So say you have it in the x, y coordinates. This is x, y, and this is 0. And let's say you have u, or a is here. Let's say a is here. This is our a. Like that, or let's make it longer here. So this is our a vector, like that. And now if you divide by its length, or you scale it down by its length, you just get over here, where this length is 1. This is going to be our unit vector. And the unit, and the length of this, so the length is equal to 1. Yeah, so this is just 1. Like that. Yeah, so I just put that 1, just saying it's a 1 distance across there. Or better yet, just put a dashed line like this, dash, da, 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 da. This length is going to be 1. So that's the unit length of that. And notice it's in the same direction as A. It's the same direction as A. Yes, fascinating stuff. All right, so now going further. So yeah, in order to verify this, that is this actually equals to 1 there, we let C scalar equals to 1 divided by the length of the vector A. So that you have this sign like that, bracket, the vertical columns, and then A vector. Then if this unit vector is equal to C, the scalar, times it by A, the vector, and yes, C is a positive scalar, so U has the same direction as A. So it's positive, it's not negative. Because right here is the length here. This is going to be an absolute value sign. That's basically saying it's greater than 0. Greater than, it's greater than 0. So it's positive scalar, and so U has the same direction as A. So then also, so this it has the same direction. This is just a positive scalar. All you're doing is scaling it up further down or smaller, etc. So it's always in the same direction because it's positive scalar. And also, and now here's where we prove it. So if we look at the distance or the length of the unit vector U, this equals to the length of the, just put these inside, CA. So this scalar times by this vector. And now this equals to, well, absolute value of C, that's, or just the length of the C, just the scalar, so then it's positive, and it's just going to be C like that, and then also times by A like that. So just factor that out, and then the C is equal to 1 over the distance, 1 over the length of a vector, and then times it by this right here, this A vector here, and these just cancel. This equals to 1. So you can just write it like that. Yeah, so basically the length of this C times A, where C is equal to 1 divided by, the length A, 1 divided by length A, this equals to length A divided by length A, this equals to, they just cancel. The lengths cancel, you're equals to 1, and we get this part right here, so check mark there. All right, and now let's go further. Before that, let's just put a check mark here. So yeah, this check mark equals to this one, and so on. So example 6. So this states, find the unit vector in the direction of the vector 2i minus j minus 2k. So it's very interesting. Now we're asked to find the unit vector in this direction of this way. So the given vector has length, because we're going to need the length, and we're just going to multiply that by, we're going to divide this vector by the length, and we could just divide it each term and so on. So what we get is, the vector has the length, and you could write it in this notation, this absolute value sign, or just a vertical column. So 2i vector minus j vector minus 2k vector. So the length here is equal to, and in 3D, you just square the components. 2 squared plus -1 squared plus -2 squared, like that. And this just equals to, well, 4 plus 1 plus 4. So -1 squared is 1, -2 squared is 4. So this equals to, this equals to, let's put it here, this equals to square root 9. So you have 4 plus 1 is 5 plus 4, or 4 plus 4 is 8 plus 1 is 9. This equals 2, and square plus or minus 3, but we're just going to look at the 3 positive. Like that. All right, there's, let's put into check mark. So that's 3 there. All right, so thus, by the earlier equation for a unit vector, the unit vector with the same direction is, so we just divide this by the length there. So unit vector is the vector divided by the length. In other words, you're multiplying it by a scalar. So the unit vector, you could write this as, the unit vector is equal to the vector divided by, so the vector is just there, 2i minus j factorial, not factorial, the vector, the arrow, minus 2k, like that. Then divide this by the length. So put this like this in notation, 2i with the vertical columns minus j minus 2k, like that. Let's make it a bit neater. Now this equals 2, and let's write this out. Yeah, this just equals to, well, this is 3. This is divided by 3. So in other words, you're just multiplying the vector by a scalar 1/3. So multiplied by 2I minus j minus 2k. Like this. And then you could, well, write this all out. So 2 over 3. Like this. 2 over 3I minus 1 over 3j minus 2 over 3k, like that. And now we could just box this out. Alright, and now let's go over the last part of this video. That's on application. So vectors are useful in many aspects of physics and engineering. In future videos, we will see how they describe the velocity and acceleration of objects moving in space. Here, we look at forces. So a force is represented by a vector because it has both a magnitude, measured in pounds or newtons, and a direction. So if several forces are acting on objects, or actually on an object, the resultant force experienced by the object is the vector sum of these forces. And that brings us to example 7. So example 7 here, it has, so a 100-pound weight here hangs from 2 wires. You have 2 wires right here, shown in the figure below. So when you have 2 wires like this is going to split up the forces according to the angles there. Yeah, for example, if you wanted if you had a rope like this, if you had a rope here that's vertical, holding a big giant ball, and then you had another rope that's horizontal, this one is experiencing no vertical force, so all the force goes to here. And then basically as you adjust this angle, as you adjust it accordingly, so you move this up, and then it's going to shift the weight accordingly. So basically, just basic geometry right here. I mean, trigonometry. You can basically do some trigonometry to see the components of the horizontal and vertical and so on. And we will get to that. So here we have T1 here is this 50-degree angle there. And this tension 2 in this cable is 32. It has a 32-degree angle there, and there's a 100-pound weight that's being held up by these 2 cables or wires. And we're asked find the tensions or forces. Tension is just being pulled, so this is being stretched apart. And yeah, T1 and T2 in terms of their horizontal and vertical components. So these T1, T2 are vectors. They have both a magnitude, the force in pounds or newtons, and it has a direction. This one's directed to the right. This one's directed to the left at this angle, at these angles, 50 and 32 degrees. All right, so let's take a look at the solution. So we first express the vectors T1 and T2, or the tensions T1, T2, yeah, in terms of their horizontal and vertical components. So from the figure below, we see that. So let's just break these down. So we have here is going to be, well, the tension here, and then, well, so this is a bigger angle. So this is 50, and this is 32. So it's more steep. So let's go like this. Just draw a triangle. This one's going to be more steep, like this. And this one's going to be more to the side, like that. So we have these angles like this. All right, so we have this angle here. This is 50 degrees. This angle here is 32 degrees. Yeah, so that is not as steep as this one. So 50 and 32. And now what we have is the tensions. And I'll draw this arrow like that, this arrow. This is going to be our T1 vector. This will be our T2 vector. And now the horizontal components, well, if you look at this right here, just using our geometry, this one right here is just a Z right here. This one has the same angle across over to here. What we could do is, this is this angle. So this has vertical and horizontal components, whereas this angle is 32 degrees. Yeah, this is exactly the same thing. This is just mirrored. So for example, if you had a Z, this angle is the same as this angle. Those are this basic geometry. Yeah, and actually I'm going to keep the Z here. So note this angle, okay, this angle is equal to this angle. It's just the exact mirror image of that. So those are the same angles. Likewise, this 50 has this angle here, so you could use it across here. Okay, draw that there, draw this here. This is going to be our across here 50 degrees. All right, so that's what we have there. Now we have the arrow down. This is just the W vector, or the weight, and that's just the W is 100. All right, so that's what we have there. So from the figure below, we see that, and we're going to break this down into its components, make this a bit better vertical line. And we could also do another note. So note that one on the Z, but also note that if you had a triangle, just use basic trigonometry. So the lengths are, so if this is, this is our A. Yeah, here. So if that's our A, this is our angle, then the horizontal one right here, this is just going to be, well, let's say it's B. Actually, let's do this as C. Let's say that's C, this is A, and that's B. A, B, and C. So then remember the ratios cosine theta is equal to A over B, and sine theta is equal to, yeah, this is, A over C. Sine theta is equal to the opposite over adjacent, so this is B over C. Like that. So in other words, you can just move the C all over to the other side. So you get A, this equals to C cosine theta, and this one here is equal to C sine theta. So we could use that for over here. So we could use that here, and we could write this out. So we could write this T1 vector. So the T1 vector in its component parts is equal to the horizontal over here, and that's going to be negative because we're gonna say this is positive, this is negative, and then going downwards, or yeah, going upwards is positive, and going downwards is negative. Like that. Yeah, here, just fix that up. So we have plus, plus, and then minus, minus. So in other words, T1 is going to equal to negative, then using the same setup where it's going to be the length T1 of this vector times it by the cosine of that angle. So that's just this part right here, C cosine theta, where the C is the length there. So C, this is going to be the length of the T1 tension times it by cosine of the angle. In this case is 50 degrees. And then that's the horizontal, and the vertical is going to be over here, and that's going to be the sine. So plus the length T1 of the vector T1 times by sine 50. Like that. And yeah, we forgot to actually add our vector. So this is, we need to put in the components parts, otherwise this is just a scalar. So we're going to have our I vector. This is going I to the opposite there. And this one's going to be J vector, like that, the standard basis vector. So we're just to say that we're doing it in, yeah, we're writing this as a vector with its components added up in standard basis vector form. Because otherwise, if you didn't have those, then you're just going to have a random number that you're summing up. So now the next one is T2 is over here. So this T2, its component parts is going to be both positive, and then it's going to be cosine 32. Now then it's going to be plus sine 32. So this is going to be equals to the length T2 vector cosine of 32 degrees. And this is going to be I vector form plus T2 arrow, and then sine. This is going to be 32 degrees J, like that. All right, so the next setup here is, well, the resultant sum of these forces, T1 vector plus T2 of the tensions or forces, counterbalances the weights as W, and we must have, so then we determine the top positive, so that means to make it equal to the bottom, which is the negative, we have to have T1, the vector, plus T2, the vector, is equal to negative W, the vector. So it's equal to the negative because here, yes, we have 100. So then this needs to add up. Yes, add up and equal to this negative of this. And in other words, actually more clear like that. So if you sum up all these vectors, so plus this W vector, this has to be 0 because it's counterbalancing it. So there's no net force. In other words, we can move this over, and then we're going to get, T1 plus T2 vector equals to negative W vector, which equals to, well, we know that W as vector is pointing downward, so that's going to be negative of, negative 100. This is going to be 100 We're going up here. So it's 100 pounds right here. So this is a 100-pound weight. It's going down, and then its vectors are, well, j. It's going to be 100, and this is going to be j, like that. So it's just vertical. So then this is going to be positive. This equals to 100 j, like that. Or even more complete, you could write this as equals to 0I vector plus 100 j vector. Yeah, so in other words, there is no net horizontal force there. There's just 0 being pulled. The weight's only going straight down. All right, so thus what we have is, now what we'll do is, well, T1, well, actually, instead of writing thus, instead of typing, I'll say thus here, just so it matches the look. So we'll have T1 vector plus T2 vector. This equals 2. Well, let's add these vectors around. So this equals 2. Yeah, this equals 2. Well, this vector plus this one, and since it's pretty big already, I'd rather not write it again. So what we could do is factor out these i's like that. Just factor out this and this. So then, and likewise for this one here. So we can just add the components. There's just vectors, so we're adding the components. So this equals 2. So you can write this as bracket negative, and then the distance or the length T1, cosine 50 degrees, and then plus this part right here, plus T2 vector cosine 32 degrees. All right, and then this is going to be our I, so we factor that out, put the arrow across, and now that's going to be the I, then the J part is going to be this one here. So we're going to factor out these. So, and then we're going to add up the other part there. And notice the angles are changing. So cosine 50 and then cosine 32. And the other one's going to be T2 sine. So T2 length sine 50. And then the other one's going to be sine 32. Plus, no, this is T1. Yeah, so the T1 and then the T2. T2, yeah, just write that out. T2 vector sine 32 degrees, and this is the times it by the J basis vector, the vertical one. And now this again equals 2. Yeah, this equals 2. Well, this right here, 0. So T1 plus T2 is equal to 0I plus 100J. So this is going to be 0I, just for completeness. Yeah, this is going to be 0I plus 100J. All right, so continuing further. So now equating components. So you have to make these all equal to 0, the components for the I, and then for the other one, the J's need to equal to 100. And solving for T1 and T2, we get the magnitudes of the tensions. So the components need to match up. So yeah, these ones right here need to match up with this. So we need to equate them. So this means that we're going to have this I component these one needs to turn to 0. And the other one needs to be 100. So in other words, yeah, we are going to get, so then this whole thing is 0 there. So negative T1 vector, the length, and then this is going to be times it by cosine. So it's going to be the the horizontal components. So those are all cosine 50 there. And this is going to be plus length T2 vector times by cosine 32. So the T2s have 32, T1s are the 50 angles or degree. This needs to equal to 0. So the components need to equal to 0 or just vanish there. And this other one needs to be 100. And now the next setup is going to be T1 vector sine 50. Yeah, so the sine is the vertical ones, then T2 is the 50 is the T1, and then the 32 angle is the T2. This needs to equal to 100. The components need to match up. All right, so now we can solve for these. Well, first one here, what we'll do is solve for T2 in this one. So we can move this over to the other side and then divide out the cosine 32. So in other words, we can get a T2 is equal to, this equals 2. Yeah, this equals 2. So T2, move this over there, is going to be the vector t1, or the length of the vector t1. It's going to be positive now. Cosine 50. And then we're going to divide by this 32. So in other words, we're going to get a cosine 32, like that. All right, so what I'm going to do is I'm going to box this. So this is the t2. I'm going to box this, and then we're going to throw this. I'm going to move this down more, do a better arrow. All right, so this goes here, and make this a bit smaller. And now we throw this inside, and that we're able to get an equation with just t1. So throw that inside, and then we're going to get a t1 sine 50 degrees plus, now we're going to get, we'll throw this inside, so we're going to get a t1 length times by cosine 50 degrees, cosine 32 degrees, and then times it by the sine 32, times by sine 32, like that. And now this whole thing equals to 100. And now this part right here, these two, just becomes, well, tan. This equals to tan 32. Yeah, so sine over cosine. Remember, that's just definition of just tan. And now we get this whole setup is, and we could factor out the t1s. So we get the t1 length is going to be equal to, so factor this out, put a bracket, sine 50 degrees plus, as we factor that, cosine 50, let's put this here, cosine 50 degrees times by tan 32 degrees. This all equals to 100. And now we could just divide this out, move it over there, and then put this in a calculator. We get t1, the length equals to. All right, yeah, so we get 100, divide this whole thing. So 100, divide this by, now we're going to get sine 50 degrees plus, plus cosine 50 degrees times by tan 32 degrees. And now this is equal to, roughly equal to, if you put this in a calculator, 85.64 lbs, or pounds. So 85 pounds. Like that. And again, this is a length or magnitude. Length of the vector is magnitude of the force. All right, I'll put an arrow here. So that is our T1, the magnitude. But now the T2, and the T2 should be less. That's one thing we should notice. That because this angle's steeper, the T1 should be larger than this T2. And now the T2, we know that is this part right here. So the T2, we could throw in our value for T1, and I'll do a calculation check soon. So we could throw the value in for T1 and then times it by cosine 50 over cosine 32. And we get, so now the next one is and T2, put an arrow, and T2 equals to, so this equals to T1, the magnitude or the length, times cosine 50 over cosine 32. So T1 vector times by cosine 50 over cosine 32. Now we throw this inside here, and then plug it in the calculator. You're going to get a value that is, roughly 64.91 lb, or pounds. And again, this is less than this one, which is expected. That's less, as expected. Because the angle is steeper for the T1, so then that means there's a bigger vertical component. And then the T2, the angle isn't as steep, so it's a less of the weight is being carried by it. All right, and now I was going to do a quick calculation check right here. So the first one, the tension T1, this equals to, and again, this is the magnitude of the tension, so it's always positive here. So 100, this is 100 divided by sine, and this one I have it, it's in my calculus, in my OneNote calculator that I'm using right now. It's right now its default is in degrees. So 100 divided by sine 50 plus cosine 50 or times by tan 32 equals 2. And if I just erase this and press equals space, so automatically calculates to this degree there. So that many decimal places, and we have 85.638. So you round that up 64. I'm going to put a check mark here. So that's right. Now the next one is right here. So T2, this equals 2. So we take our value, I just put that whole thing, copied and pasted it right here, and times it by cosine 50 over cosine 32. And what we get is, to show you, press equals space, automatically gives us this. And this has, look at the decimal places, a lot, so 64.910, and you round that over. So this is correct. So calculation has been checked. So now substituting these values in the earlier vector representation, we obtain the tension vectors. So if we go all the way back up, and we have our T1 vectors equal to negative Ti cos 50 degrees times I plus T1 sine 50 degrees, sine 50 degrees J. So this is negative T1, the other ones will be positive. So let's write this out just for completeness. So T1 vector, this is the vector form, equals to negative the length, the magnitude of the force or tension, times by, this is the cosine 50 degrees I, and then plus T1, the length, sine 50 degrees J. And now if you plug in the calculator, you get roughly equals 2, or actually I'll just put that right here actually. Let's plug that in. This is going to be equal to, so when you plug in the values of these ones here, inside here, and solve it, we get, we get, I'm going to round this up, it's going to be approximately negative 55.05 I plus, and then the 65.60 J. And I'll do a calculation check soon. So that is for, that's for T1. Like that. Now T2, this equals 2. Well, it's going to be the positive T2, the absolute value, or the length. So just the length of it, or the magnitude, times by cosine, now we do the 32. I plus T2, and then this is going to be sine 32 J, like that. And again, you could just see that right over here when we wrote that over. So this is the cosine 32 and then sine 32, and it's all positive there. T2, and then plug that into the calculator. You're going to get roughly equals 2, and it's going to be 55 also, but positive. 550 I. And again, notice how it has to equal to this one, because remember we had a 0 I, so this one has to be the same as this. So they cancel. So notice that they're exact same ones when you plug into the calculator, which is quite fascinating. And now the next one is going to be plus, and then this would be 34.40 J. And notice this right here. I'll box this out. Yeah, so notice these right here, and I'll do the calculation check soon. This one here has to add up to be equal to 0, so 0 I. And then this one right here, or just put an arrow, yeah, so these two goes down to 0 I. And this one here, just quickly, for some reason my OneNote just erased everything. But anyways, so this one right here, when you add these up, 65.6 and 34.4, that's just 100. In other words, we get right here 65.60 plus 34. Let's write it a bit thicker. 665.60 plus 34.40 is equal to 100. Because you have 60 plus 40 is as an extra 1, so 66 plus 34 is 100. So yes, so that is 100. And this one right here, we get a negative 55.05 plus a 55.05. This equals to 0. So yeah, that goes to 0, this goes to 100. fascinating stuff. And yeah, here, just fix that up and just wrote it better than circle line. Yeah, so that equals 0, this equals to 100. So it's just interesting. So it's an interesting visual check. All right, and now finally, let's do a quick calculation check over on these ones. Because yeah, this is when you plug in the calculator, you get these. So this T1 cosine 50 and it's negative sign. So negative T1 cosine 50 degrees equals to, well, the magnitude of T1 is over here. So I just use the full decimal places here in the calculation. This is 85.64, or copy that into here, times by cosine 50. And what you get is negative 55.047, round that up to 0.5. So that is correct. The next one is T1 sine 50, so the same one there. Put it in here, sine times it by sine 50. So you could erase this and press equal space, and it gives you 65. So yeah, my OneNote has a built-in calculator, which is quite amazing. This was 65.6026, and yeah, rounded up, 60. Or actually, that's rounded down. Next one is T2 times cosine 32. So that's this T2 right here. And we got 64.910 or 64.91. And use the full decimal places just to make it more accurate. Put that in here, times by cosine 32. And we get that 55.047, exactly this one actually. But here, because you did the calculations a bit differently, this is the last digit 7, this one is an 8, so interesting way of computing stuff. So anyways, that's correct, 55.05 when you round it up. And then now this T2, yeah, so I don't know why this got so big. So now the next one is T2 sine 32, and there's the same one, the T2 times by sine now, 32. Just to show you, equal space 34.397, rounds it up to 40 and so on. Yes, we're just quite fascinating stuff here. So no, yeah, these ones would cancel, I go to 0. This one adds up, goes to 100. Yeah, and here lastly, I just added these numbers here. So I added this one here, this one here. So notice this 8, there's a 7. And then this one here, and then this one here. And I'll just do the calculation check. We'll go equals space. So yeah, this is 1. It's a negative 1.0 times e. This is just stating 10 to the power of negative 14. Yeah, so this is 10 to the negative 14. In other words, that's very, very small. That's basically saying 0. Well, it's a negative 0, 0, 0, 0. So it's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and there's a 1. So that's how accurate the calculator is. And now this next one is equals, whoops, the next one, let's put a space, equals, yeah, so this one also goes very, very accurate, 99.9999999 all the way to the 4. Yeah, so in other words, rounds up to 100. And yeah, this is basically, because the calculator is just showing you how accurate it is, but this just equals to 0. Yeah, well, actually, this does that automatically. So this equals 0, this equals, I'll just put a, see, it automatically puts that, equals 100. Or I'll just leave it like that. So yes, this is very, very accurate. Anyways, that is all for today. Hopefully you enjoyed this, another deep dive into vectors. And yeah, so this is part of the geometry of space, and so on. Interestingly, in the first video, I wrote vector space and geometry as a title, and I realized, why did I do that? That's nowhere. Doesn't make any sense actually, and it's not. Yeah, so and then I just started changing all of the video titles and so on back to the normal one, which is the vectors and geometry of space. So yes, that's pretty interesting. So that is right here, vectors and the geometry of space, actually, yes. Before I just had a vector space and geometry for some reason. Anyways, that is all for today. And again, like always, you can download these exact notes and link in the description below, as well as an article format on the Hive blockchain, also in the link in the description below. Anyways, thanks for watching and stay tuned for another Math Easy solution.